In today's video, we're going to discuss carbon and its compounds. In the early history of chemistry, chemists had discovered that molecules derived from living sources, so from plants and animals, tended to behave and react differently than molecules that were derived from the natural world, so ores and minerals and that type of thing. And this was the first distinction of what they called organic chemistry, which they associated with living things, and inorganic chemistry, which was derived from basically everything else, the non-living world, so to speak. They also noticed that these quote unquote organic compounds via analysis tended to have always a very small subset of elements that made up these compounds. Notably carbon, hydrogen, nitrogen, oxygen, sometimes the halogens, and maybe just a few more handful of elements. And so this is where we begin when we are talking, when we're just first talking about organic compounds. The definition of organic chemistry today is the study of carbon and its compounds, and because carbon is at the center of all organic compounds. And so the other thing they recognized was that these particular different elements, these organic elements, tended to form a certain number of bonds, and this was fairly regular. So for example, they noticed that carbon typically formed 4 bonds. As you can see here depicted by these various different molecules here. They might be multiple bonds, they might just be single bonds, but if you count the number of lines to each carbon atom, they always amounted to 4. If we go over to another organic element, such as nitrogen, they found that nitrogen tended to form 3 bonds. Again, you'll notice here that the 3 bonds can be made up of single, double, or even triple bonds. And then continuing along, they found that oxygen tended to form 2 bonds, and then hydrogen and the halogens tended to form 1 bond. And this was the start of their basis of being able to piece together what these particular organic compounds look like, based on what we call these valencies or valence rules. And this is referring to the number of bonds that these different elements typically formed. And so basing this on the valencies of these different elements, then we can now develop what we call Lewis structures for these organic compounds. This should be hopefully a review from your first year chemistry. Here is sort of a list of different, I'll say, instructions or steps to follow in order to develop Lewis structures. But what's important here is that you have a good handle on being able to draw Lewis structures quickly and obviously correctly. This is where we start. So we'll do an example here. If you look at this first compound, the connectivity is implied here. So we've got 3 carbon atoms. So we'll look at this first structure here. And when we draw a Lewis structure, typically what we do is we draw all the bonds and all the lone pairs on the atom. So everything is shown explicitly. So I'll start off with my first carbon atom, and we'll develop from there. Actually, first thing we should do is actually calculate the number of valence electrons we have at our disposal in order to develop this particular Lewis structure. So we start off here with carbon, and we ask ourselves basically how many valence electrons can this element bring to this structure. The valence electrons are essentially tied with the group number of the different elements, and so carbon is in group, this is older nomenclature, but carbon is part of group 4, and so carbon brings 4 valence electrons per carbon. So we have 3 here, so we have 4 electrons for each carbon times 3, and therefore this brings us 12 electrons. Hydrogen is in group 1, and therefore it has 1 valence electron, and we have 3, 5, 6 hydrogen atoms here. And then finally, we have one oxygen atom. Oxygen is in group 6, well, it's actually 16, but the older nomenclature is group 6, and so therefore it has 6 valence electrons. 1 is equal to 6. So if we add this up, we have a total of 24 valence electrons in order to distribute to develop this first Lewis structure. So typically what we do is we just start with the carbon skeleton. And so I know I have a carbon here. I know it has 3 hydrogen atoms attached to it. That's the CH3. And then now I have a CH2 group. So this carbon is attached to the next carbon. And there are the 2 hydrogens attached to it. And then I finish off by saying this carbon, it has a hydrogen and an oxygen atom attached to it. And so we start off by just drawing basically the skeleton of this particular structure as it's been given to us. And we just include single bonds at this particular moment. What we want to do now is count the number of electrons that we've used of the available 24 electrons that we can use. So we recognize that a bond, any one of these lines, represents 2 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've used up 18 electrons forming these single bonds. And so I can subtract that from my total here. And this leaves me with a total of 6 valence electrons still that I have yet to distribute on this molecule. If you just go back to our steps here, and if we look at, step 2B here, so we subtract the number of bonding electrons from the number that we had originally calculated. We just did that. So we now have 6 electrons left. So it says any electrons that are unpaired are added to atoms that lack a full octet, typically heteroatoms. So we do have a heteroatom here, oxygen. Recall a heteroatom is anything other than carbon and hydrogen. And I have 6 electrons yet to distribute. I'll notice that oxygen is only taking part into 1 bond so far, and therefore it only has 2 electrons around it. So if I put 8 or 6 more electrons around it, it will now have a complete octet. Okay, so I've now added the last 6 electrons, and I have no more electrons to distribute. But we're not done now. Now what we need to do is assess our Lewis structure, and we need to determine whether or not this is the best Lewis structure. All the hydrogen atoms should only have 1 bond or 2 electrons around it. They all meet that requirement, so they are good. If you look at the left-hand carbon atom and the central carbon atom, you'll see that both of those are forming 4 single bonds and therefore have 8 electrons around it. So it's met its valence requirement, which is 4, and it's following an octet of electrons, which again is something that carbon would like to do. The carbon attached to oxygen, however, you'll notice that it's only involved right now in 3 bonds. They happen to be 3 single bonds. So therefore, there's only 6 valence electrons around that particular carbon atom. So that carbon atom right now is electron deficient. And then if we look at the point 2C here, it says atoms still lacking an octet are satisfied by using lone pairs from adjacent atoms to form multiple bonds. So this is the situation we're at right now. We have an atom, this carbon atom here, which is lacking an octet. It does have an atom directly adjacent to it, which does have a lone pair. So what we're going to do is we're going to take one of these lone pairs. It does not matter which one. And now what I'm going to do is instead of leaving it as a lone pair onto oxygen, I'm actually going to put it in between the oxygen and carbon atom to form a bond. Now, because there's already a bond there between carbon and oxygen, this will now form a double bond. So I will just redraw this here. So nothing has changed over here. And now what I've formed here is a carbon-oxygen double bond. So now you'll notice that if we look at the number of electrons around all our atoms, they'll all satisfy the octet or the 2 electrons that we need around hydrogen. That carbon, which was electron deficient, notice now that it is taking part in 4 bonds, so a double bond and then 2 single. It does now have 8 electrons around it, and therefore and is happy, and that oxygen still has 8 electrons around it. And again, oxygen typically likes to form 2 bonds, and you can see that we have 2 bonds here to oxygen. So this is our final Lewis structure. And before you finish off, you should always make sure that your Lewis structures, that you actually calculate the formal charges of all the different atoms. Just because the molecule is neutral overall does not necessarily mean that there's no formal charges. In this particular case, what you'll find is that all the formal charges for all the atoms are equal to 0. But this is an exercise that you should go through to make sure that all these atoms have a formal charge of 0, as they do in this particular case. So that's one example. The others we'll look at during one of our live meetings. Okay, let's talk a little bit about bonding in organic compounds. So these lines that we draw in between these different atoms, these single, these double, these triple bonds that we draw them, these are known as covalent bonds. And the covalent bonds are essentially a sharing of electrons in between 2 different atoms. And so we can show you this particular type of bonding and how this arises from the overlap of the different orbitals that are involved. This should be a review from your first year chemistry. And just recall that, because we're dealing with organic elements, carbon, hydrogen, nitrogen, oxygen, we're typically only generally going to talk about s orbitals and p orbitals. And so all we need to do is remember how these particular orbitals can overlap with each other. So just recall that in a sigma bond, so we use this Greek symbol here of sigma, we have essentially a head-on overlap between either 2 s orbitals, 2 p orbitals, or an s and a p orbital, okay? Now, in this particular example, they've actually gone ahead and used the hybrid orbitals, which we're going to talk about a little bit later. It essentially looks like a p orbital, however. And so what we're saying is we have this s orbital here, and then we have this lobe of so this lobe here of essentially this sp3 hybrid. And if you overlap the end of the s orbital with the end here of the p orbital, as long as they have the same phase, then you will get constructive interference, i.e. you'll get an actual chemical bond. And that's what they're trying to show you here in this picture here. So what they've shown you here in this sort of pink or purple sort of color is the net, what the orbitals look like after they've overlapped, after they've had this constructive interference. Okay, you can see essentially that the lobe has kind of gotten bigger. So now you've got one lobe because the S and P have kind of mixed together, creating this larger lobe. Okay, now the thing to really look for here is I want you to look at the areas in between the nuclei of these particular different orbitals. So the s orbital, the nuclei here is given as a small green circle. Same thing here for this sp hybrid or the sp3 hybrid or the p orbital. And if you look in where they actually have the bond here and in between these 2 nuclei, you have an area of overlap with the orbitals, and that means a bond. Okay, there's no node there. And by a node, we mean a 0 probability of finding the electron. Remember, these orbitals, what they describe, an orbital is nothing more than a mathematical model that describes the likelihood of finding an electron in that area of space. So in this particular sigma bond, we've got this now lobe in between these 2 different nuclei, and it's telling us then that we have, the probability of finding the electron is in between those 2 different nuclei. We can get the same type of bond, a sigma bond, by having either 2 p orbitals or 2 sp3 hybrids overlapping. So again, you can see you've got a shaded lobe here and a shaded lobe here, and they're coming together to overlap. And then when they add together, you get constructive interference. So you get something that looks sort of like this. Again, these are more like computer graphics of this. This is just a way for us to visualize. But what's important here again is if you look the area between the two nuclei, that there is an actual overlap there, which meaning that there's a bond. If we were to look at, for example, the overlap of, if we look at an anti-bonding combination here, so if you had a p orbital and another p orbital, but now the phases don't match, so if you add this like this, then typically what we get is something that looks like this. And here I'm going to shade in the nuclei of each of those two different atoms. And you'll notice now that there's an area right here that I'm putting a line through where there's no actually overlap of the orbitals. This is called a node. And this is important to recognize those areas in between the nuclei, because if there is overlap, then that means there's a bond. And if there's no overlap, i.e. a node here, means that it's not a bond, i.e. it's an anti-bonding interaction between these orbitals. So we can have two s orbitals overlap to form a sigma bond. We can have an s and a p orbital that overlap to give you a sigma bond. You can have two p orbitals or even these sp3 hybrids, which look very similar to p orbitals. And they can all overlap in a head-to-head fashion to give us sigma bonds. How do we get pi bonds? Well, this is when these orbitals interact, instead of a head-to-head fashion, they interact in a side-to-side fashion. And of course, this can only happen with p orbitals or d orbitals and so on and so forth. We can't have side-on overlap with the spherical s orbitals. So here they're showing you two p orbitals. It's unfortunate that they've got the shading, the two colors of the shading being very close. So on top here, they have more of a purple color, and on the bottom, they have a blue color. The point is, when you have overlap with these two orbitals, notice that they're coming together a side-to-side fashion, right? So these two purple lobes will interact, or they will have constructive interference, and these two blue lobes of the other phase will come together in a side-to-side fashion to have overlap. And this gives here now, so you can see there's this region here. So now we've got this constructive interference here on top and on bottom, and this is known as a pi bond because of the orientation of the two different bonds, or I should say the two different orbitals, how they came together. Again, you can see they've got the node defined here, and they still have them here in the pi bond picture. And p orbitals inherently have a node. So there's a node here in this p orbital, and there's a node here and here in the second p orbital. So that means there'll always be a node in pi overlap. That's just inherent because of the p orbitals. But what I want you to look at is this area on top here, where I'm drawing a line, and you'll notice that there's no area there where there's no overlap. There is overlap here, and i.e. this is a pi bond, an actual bond. If we had these two p orbitals come together in an anti-bonding fashion, so now what I'm going to do is I'm just going to flip the phases of one of these p orbitals. If we have something like this, then what we have is they kind of bend away from each other. So there's our node. So we still have this nodal plane here, but that's again inherent from the p orbitals. But what I'm more interested here is seeing that now there's a node in between those two different lobes, and that's an area of zero probability of finding an electron, and therefore this is not a bond. This is an anti-bond. We're going to get back to these orbital pictures a little bit later on when we start talking more about pi bonding. Another concept to look at here is this idea of dipoles, and dipoles are nothing more than electronegativity difference between different atoms, bonded atoms essentially. So what we have here is a very small number of elements. These are like typical organic elements, And we've included here, this is from the periodic table, and they've included here the Pauling's electronegativity values for them. And basically, the greater the difference between these two atoms, those values, the bigger the the bigger the electronegativity difference, and therefore the stronger the bond dipole. So what we have here in this picture is what's known as an electron density map, so to speak. And so you've got, it could be different colors, but in this particular case, they're kind of shading a green. And they're trying to give you an idea of how the electrons are distributed over this carbon-hydrogen bond, okay? Carbon is more electronegative than hydrogen, not by much, but if you look at the values 2.2 versus 2.5, there is a small electronegativity difference between these two atoms. So it would make more sense that there would be a little bit more electron density around carbon than there would be around hydrogen. And this is why that sort of green sphere or blob, if you will, on top of the carbon atom is slightly bigger. If these would have had the exact same electronegativity, then this green cloud above these atoms would have been symmetrically distributed, and it's not. So it's one way of visualizing this bond dipole. Another way is to just write in these partial charges here. So they're using the small Greek letter of delta. And so whenever you see a delta, we mean a partial. So this means that there's a partial positive charge on hydrogen, a partial negative charge on carbon. And yet another way of doing this is just to draw sort of a vector or a dipole, in this case, showing you the direction of, where the electrons are pointing. And in this case, they're pointing in the direction of carbon. They are all showing you the same thing. Now, even though there's an electronegativity difference between carbon and hydrogen, typically for most organic compounds, we kind of consider carbon-hydrogen bonds to be essentially non-polar. They are very slightly polar, but for all intents and purposes, we consider them to be non-polar. If we look at a more extreme example of this, so let's just look at an oxygen-hydrogen bond. So again, if you go back here, you can see here that there's a much bigger electronegativity difference between oxygen and hydrogen versus carbon and hydrogen. And so if you look at this electron density map, notice that there's a much bigger green cloud around oxygen than there was around the carbon when it was a carbon-hydrogen bond. And this is reflecting that greater electronegativity of oxygen. So again, we could represent this bond as, delta plus, delta minus, or as this vector. Again, you'll notice that this vector that they've drawn here towards oxygen, notice that the line, the arrowhead itself is just bigger. Like this line is just generally bigger in this example than this one. And that's to try and show the magnitude of that dipole. So oxygen-hydrogen bonds are definitely considered to be polar bonds. The reason why we're interested in whether bonds are polar or very polar or non-polar is because understanding this allows us to predict the structure, the properties, and even the reactivity of these organic molecules. So having an understanding of this, again, we're basically talking about, where are the electrons distributed along this molecule? Having that knowledge gives us a better understanding of their physical properties and reactivity. Okay, so we've talked about how the typical valencies of these atoms. So we typically say, in organic chemistry, that if you can count to 4, you're good. So 4 bonds to carbon, 3 to nitrogen, 2 to oxygen, 1 to hydrogen and the halogens. We can also use Vesper theory in order to explain basically 3, there's only 3 here, general shapes that we typically see for these organic elements. And so basically the 3 shapes are linear, trigonal planar, and the big one here is tetrahedral. So in a linear geometry, this is typically when we have triple bonds involved. So a great example of this would be this acetylene molecule here. So you can see that both carbon atoms, they're part of a triple bond. They still have 4 bonds, but they're not part of a triple bond. And this bond angle here is typically about each carbon atom is about 180 degrees, making the molecule linear. If we have carbon, which is involved in a double bond and two single bonds, then we typically get what's called a trigonal planar geometry. So again, it's like three electron groups, so to speak. So in this particular case, an oxygen and two hydrogen atoms pointed at about 120 degrees away from each other in the same plane. And that's where the name planar comes from in this geometry. And then finally, when carbon is involved with four single bonds, the easiest way of getting those electron groups about that central carbon atom would be to put them into a tetrahedral geometry. And so those are the three typical geometries that we explore in organic molecules. So again, you can see here, they're just highlighting the linear aspect of carbon when it's involved in these triple bonds. And you can see here, they're highlighting the bond angle of 180 degrees. So again, we're just using simple Vesper theory here. We're saying, look, there's two electron groups. So if you look at, say, for example, this carbon atom, we have two electron groups about that carbon atom, a hydrogen atom and a carbon. And how can we get them as far apart as possible? When there's two electron groups, the easiest way of doing that is putting them 180 degrees apart from each other. And this is typically what we see. And the bond angles for these triple bonds are 180 degrees. And that portion of the molecule anyways is typically linear. Same thing here when we have trigonal planar. So when we have carbon involved in a double bond with two single bonds, again, how do we get these three electron groups distributed as far apart from each other around that central carbon? Well, we keep everything in the same plane and we put them at about 120 degree bond angle. It forms this triangle, and so this is where the term trigonal planar comes from. So it forms this triangle sort of shape, and it's all in a plane, and they're trying to highlight the planarity of that carbon atom in this picture here. And then finally, when we get to four single bonds around the carbon, it likes to form this tetrahedral geometry. This one's a little bit more, perhaps a little more difficult to visualize because this molecule is no longer planar. It is actually, it does have some three-dimensionality to it. So the way they're showing you this particular structure here, you're going to have a couple bonds that are in the plane of the screen or the paper. So in this particular case, from the drawing above, this bond here and this bond here are in the plane of the screen, and then the wedge. So this particular group here is coming towards you, and this one here is slightly pointing away from you. The fact here, though, is that understand that because we have four groups and this molecule is not planar, we have bond angles of 109.5, and this is the best way we can do that to avoid any electron-electron repulsions. Now, one of the things we need to do, and this is what we're going to finish with, is that when we deal with tetrahedral carbon atoms, and we're going to see this a lot, we want to try and show as best we can the three-dimensionality of that carbon atom. And so this is why we do use this, for example, this wedge here and this dash, and that's to show that the group is either coming towards you or pointed away from you in the plane of the paper or screen. And it's just important that you get a feel for how to use these dashes and wedges. So again, what you need to remember is that when you're looking at a tetrahedral carbon atom, typically the way we orient the carbon atom or the rest of the molecule is that two bonds are in the plane of the screen or paper. And so in this example above here, it's these two upper bonds. They're just drawn as simple lines. So I know that they're in the plane of the screen. And then the other two bonds will be a dash and a wedge. The other thing to notice is that if you look at the two bonds that are in the plane in this example, they kind of form a V. And this will typically be what we see. And then what you want is that V is essentially kind of pointing up right now. And so your dash and your wedge in this case should be pointing in the opposite direction. And that's what this note here is trying to show you. So the dash and wedge should also be in a V, but they should be basically, pointing in the opposite direction as the other V of the two bonds that are in the plane. And typically we have the dash and wedge a little bit closer towards each other than normal bonds. So it should look something similar to this. If ever you have all your hydrogen atoms pointed in the same direction, then you're going to run into problems because this is not depicting a tetrahedron. It's depicting some highly strained sort of geometry around carbon atom. The thing to remember is that you can rotate these different tetrahedral carbon atoms. So there's no rule, so to speak, that says that the two bonds that are in the plane have to be pointing in a particular direction. So pay attention to these four tetrahedral carbon atoms that have been drawn here, and just look at, where the dashes and wedges are placed, and in relation to where the two bonds are that are in the plane of the paper, and how they're placed. So, like, for example, here, the two bonds in the plane could be pointing down, and therefore your dash and wedge will be pointing up, or that can be reversed, as in this case here. But again, they don't have to be either pointing up or pointing down. They can be kind of pointing to the side, as shown in these two examples. So just understand that all four of these are completely correct. All we've really done is just rotate the different orientation of that tetrahedral carbon atom.